Here we go with entropy for chemistry today. So there's entropy and enthalpy. So we're going to review enthalpy first to make sure we're all keeping them separate. Enthalpy, TH, like thermal. Okay, enthalpy, thermal, endothermic, exothermic. Okay, endothermic is a positive, so it's on the reactant side because we took energy in for something to happen. Exothermic, we exited or the energy was released. So that is negative. It's no longer in our reaction. Okay, and so we can think about solids over here vibrating in place. Gas, fast moving, chaos, okay? Which one is going to have more energy? That gas is going to have more energy, so it's had to take in more energy for each phase change. To go from a solid to a liquid, for that ice to melt outside, the sun had to heat it up. To go from a liquid to a gas, you put that water on the stove, you turn on the stove, you heat up the water to go from a liquid to gas. So enthalpy is going to increase, or we're going in the positive direction, the endothermic direction when we go solid, liquid, gas. And the other direction is the exothermic direction. Heat had to leave. And that's actually the easier way, or what's called the favored way to go. So even though this is not a chemical reaction, it's still good for when you're trying to figure out what's happening with phase changes. And it still does apply for chemical reactions as well. Now we have entropy, which is measured with an S. Okay, and this is all about chaos and disorder. Okay, so chaos ends in S, entropy symbol is an S. If you have positive entropy, you have chaos. Okay, positive entropy, you have chaos, because that is disorderly. As the universe goes on, which sign are you going to have, the orderly sign or the chaos sign? It's sitting there, it's being exposed to the weather. So the chaos sign is what naturally is going to be happen as you go on. We're increasing the chaos, we're increasing the disorder, and that is a positive sign. So when entropy increases, we have chaos. Right, so we have the same type of thing, and now we're thinking about it in terms of entropy. Is it organized or not organized? Gas, random, solid, crystalline, specifically shaped out. Solids have more order than gases. Okay, so the entropy increases when we go to disorder. Entropy is about disorder. So now we're going to try to frame everything in terms of disorder. You probably have learned to think about keep it neat and organized, and it's all about being orderly. But for entropy, it's all about disorder. So gases have more entropy. Solids have the least entropy, or the entropy decreases as we convert from a gas to a liquid to a solid. Okay. Same thing happens. Gases are close together and they're going to spread out over time, so entropy increases. The brick wall was nice and orderly here, but eventually it fell apart. Entropy increases with time. So if you don't know which way it's going, your default thing is entropy entropy increases with time. So disorder increases with time. This is the one just to write down if you have to go through very specifics. These are the ones where you are going to see more disorder. This is what happens when entropy increases. Okay. This is the opposite. This is what you're going to see what entropy decreases, when it becomes less disorderly. And we're going to go into a couple instances over here. So sugar dissolves in tea. So you had nice little happy water going on, and then you added in some sugar. So you added some disorder to that system. So when solids are dissolved and you get an aqueous solution, you are increasing your entropy. Frost forms on a window. What is frost? Frost is when it's going from the liquid stage to the solid stage. Solids are more orderly. So solids are less disorderly. Next one, air is pumped into a car tire. So you have the car tire there, and then we're adding air. We're adding air. That means we're stuffing more and more things in there. We're increasing the pressure. Okay, so when I think about increasing the pressure, I got that coal and I'm squeezing it. It's going to become that nice little crystallized diamond shape. So when I'm adding that pressure in, I'm making it less disorderly. Now, helium is under pressure in a tank, and we're going to inflate a balloon. Now I got to figure out, where's the pressure going? Where is there more pressure? Oh, there's more pressure in the tank. That tank is pressurized. So we're going from high pressure to low pressure. Well, now the pressure is literally off. Literally off. I am not as orderly anymore. I'm not all stuck in a one specific frame. Okay, so I have more disorder. Dry ice sublimes. So now we got to remember, oh man, what's sublimation? Sublimation is when it's going directly from a solid to a gas. Okay, now you're like, does that add anything? Nope, it's still that same direction. It's going to be more disorderly because it's going towards the gas direction. So we're increasing our entropy. Acetone evaporates from nail polish remover. Evaporates. What's evaporating? It's going from a liquid to a gas. More disorderly. More disorderly. Okay, so each time think about which direction it's going for the physical change or the pressure, any of those things to help you do that. And just remember, delta S, chaos. More delta S, more chaos. All right, so what if it's in a reaction? The number one thing is, if you have more moles of gas, then it's going to be more disorderly on that side, right? And then there's a couple other variations that are written up on here, but I want you to think of it like laundry on the floor. Okay, at the start of the week, your room is nice and clean, but after going to school a couple of days, maybe you didn't like this outfit, maybe you never got your hamper back when you did wash, and so it's still sitting in the dryer. So where are all your dirty clothes going? On the floor, on the floor, on the floor. So over time, we're increasing chaos. That's the natural state. But if you have more things, you have more disorder. So if there's more moles of gas on the product side, we've created more moles, so we've created more disorder. So that's the number one thing you look for. Where is the more moles of gas? And then we go through the whole rest of the checklist that I put up earlier to see what else happens. So let's go through some practice. Again, every time you want to do it, more moles of gas. On the product side, more disorder, because we're all going in time. So the more moles on the reactant, or the more moles on the product side, means that you created more disorder. So synthesis of water. Don't just sit there and try to decide, oh, synthesis is always this. Go back, and if you can, then do a chemical reaction. Make sure it's a balanced chemical reaction. What these entropy units and enthalpy units sometimes try to trick you is they do not balance the chemical reaction. So do balance it every time before you go to looking for the moles of gas. So when we are here, synthesis of water, hydrogen gas, oxygen gas equals liquid water. Okay, there's no one here. Put it in so that you don't get confused. I have 2 + 1 moles of gas. So 3 moles of gas on the reactant side, no moles of gas on the product side. 3 to 0. We went down in our disorder because we have less laundry on the floor. We started out with 3 pieces of laundry. We ended up with 0 pieces of laundry. We put everything away into a liquid state. Okay, so then we have less disorder. So we have delta S is negative. The second one, hydrogen gas changes into 2 hydrogen ions. That's still in the gas state. So we're still comparing gas to gas. We're still comparing moles. Remember, moles are the coefficients. Only the coefficients matter. Okay, so it doesn't matter that one's diatomic and one's not. Doesn't matter at this point if one's an ion, one's not. The first thing you check is moles of gas. So we have more moles of gas on the product side. So we have more laundry on the floor at the end. So we have increasing disorder. Ammonia synthesis. And again, this is how they're going to give it to you on the SOL. And you're going to go, why are they mean like that? Make sure you balance the equation first and add a 1 over here so you don't accidentally forget. Okay, nitrogen gas plus hydrogen gas gives me 4 moles. And I only get 2 moles of ammonia out of it, 4 to 2. Less laundry on the floor. Then what happens? Less chaos, less entropy. Next guy, 2 to 1. Okay, so where do I have? More moles to start. So I have less moles, less disorder. Calcium carbonate breaks down into calcium oxide and carbon dioxide. That is a polyatomic decomp rule. And there, you're lucky they gave it to you. They could have just said, what is the decomposition of calcium carbonate? And then again, instead of just memorizing what synthesis and decomp do, because they're not 100%, always still go back and change. I have 1 mole of calcium carbonate breaking into 1 mole of calcium oxide and 1 mole of carbon dioxide, but there's only 1 gas here. So I'm going from 0 to 1 moles of gas. So what is that going to tell us? More gas, more moles, more disorder. Okay, sodium and chlorine make sodium chloride. I don't have any gas there. Uh-oh, I got to go back to my other rules. Check the moles in general. All right, 1 mole of sodium ions plus 1 mole of chlorine ions equals 1 mole of sodium chloride. Well, that wasn't helpful. Okay, so sometimes you can't even go with moles. Okay, so if moles of gas isn't there, then the next thing you go is more moles in general is more disorder. And then the next thing that you got to go is check the states of matter. What is going on here? Aqueous, solid. For this, just for your brain, not in real life, if you see aqueous, picture it as a liquid. Because what is it? It's something dissolved in a liquid and it's becoming a solid. So even though we know if I have something dissolved in the liquid, when I have these ions in the water, I'm getting more disorganized because I have more stuff in there. Still going to help me make sure I'm on the right track by just looking at it as a liquid. So if I'm going from a liquid to a solid, I'm getting less disorder, less entropy, less chaos, because that sodium chloride is going to be that perfect little salt structure with that alternating negative and positive all throughout the cube. Okay, so that kind of makes sense, right? The solid is the most orderly, so it's the least disorderly. Hydrogen gas and bromine gas yield hydrogen monobromide. Okay, so they're all gases. Oh, I got 2 moles of gas on the left to 2 moles on the right. Okay, I have a balanced chemical reaction. Yep, so I check that. I check the states of matter, we're all gas. I look for the more moles of gas on the product. Nope, they're equal. I check the moles in general. Nope, they're equal too. Man, I'm running out of things to do. There's no state changes. There's no mole changes, no anything. This is your last resort one. Check the complexity or check the bond. So remember, we have information about what is happening when something is breaking or forming, and we have complexity helps us with disorder. So the rule is when it's more complex, it is going to have more disorder because we have more stuff that is going on, more complex things that are going and being created. And that's all for today.